Thank you. All right, good morning, everyone. Let's see.
Good morning, Mr. Yang.
Morning, morning. So we're going to be doing a little bit of review with Riemann sums, and then we're going to move into finding exact area under the curve. I probably need to send out a message here. I didn't get a chance to get to trapezoid rule, so your homework is just going to be page 263. That page 310 with trapezoid rule, we're not going to get to till tomorrow. Okay, so your homework is just going to be this first portion, not the second portion. All right, I want to start off by going over a homework problem from yesterday. So yesterday we went through some of the problems on page 7, which is a printout from that includes some of your homework problems. If you go to the next page, this is number 29, which is from your textbook, from your homework problem, but it was also, I copied it onto your page 8 of your packet. So the directions for 29 says, use left and right endpoints. So we're going to do left rectangles and right rectangles, approximating the area under or in the region. Okay, so the first thing that we're going to do is we need to find the width. Okay, so the width is b minus a over n. Okay, our a value is 0, our b value is pi over 2, and then our n value is 4. Okay, so width is pi over 2 minus 0 all over 4, which is just pi over 2 all over 4. Dividing by value is same thing as multiplying by the reciprocal, so this is the same thing as multiplying, get that complex fraction resolved here, multiply by 1/4. Okay, so this goes away. We're left with pi over 8. Okay, so pi over 8 is our width. Let me draw what the graph looks like a little bit here. Cosine starts at 1 and it's going to slope downwards. Okay, we're starting at 0 and we're ending at pi over 2. We're going to create 4 subintervals here with 4 rectangles. 1. And then each subinterval, we're going to add a width of pi over 8. So 0 plus pi over 8 is pi over 8. Plus pi over 8 is 2 pi over 8, which is the same thing as pi over 4. Plus pi over 8 is 3 pi over 8. Plus pi over 8 is 4 pi over 8, which is the same thing as pi over 2. Okay, let's start off with left rectangles. We know that area of rectangle is formed by width and height. We know the width is all going to be pi over 8. Now left rectangles, we're going to purposely choose the left endpoint of every subinterval, right? So here's my first subinterval, second, third, and fourth. My first subinterval, I'm going to choose f of 0 and not f of pi over 8 because I want the left endpoint here. So from 0, I'm going to go to where that vertical line hits the graph, highlight that point, and draw my rectangle there. Okay. For my second interval, I'm going to use pi over 8 attached to the curve. Pi over 4 is going to be the height, where the height is going to come from for my third rectangle. And the fourth rectangle, 3 pi over 8 is going to be where my height is going to come from. Okay, so left rectangle, pi over 8 times f of 0. F of 0 represents the height of my first rectangle that I'm going to be finding in a moment after I get everything set up. Okay, second rectangle also has a width of pi over 8. Height is now going to be f of pi over 8. Third rectangle, width is still pi over 8. But my height, my third rectangle, I'm going to be using f of pi over 4 because I want to use the left endpoint of each subinterval. Fourth rectangle, I'm going to use the height determined at 3 pi over 8. Okay, so now we're going to take the time to enter each of these values into the function, into the x value of the function to get the height component, right? To get the exact height, because right now this is all sitting in function notation. This is telling us what to do, but we haven't found the actual height value yet. So enter into the function. Now, these are all in terms of pi here, so we want to make sure that if you enter this in the calculator, that you're in radian mode. Right, we don't see like 15 degrees, we don't see 45 degrees, right, we don't see 85 degrees. These are all going to be in terms of pi, so radian mode. So in the calculator here, f of 0, if I plug 0 for x, cosine of 0 is 1. Okay, plug pi over 8 in for x, cosine of pi over 8 will give us a decimal value, 0.924. F of pi over 4, cosine of pi over 4 is root 2 over 2, which is around 0.707. Cosine of 3 pi over 8 gives us decimal value 0.383. So now we're just going to do width and height. All this can go in the calculator. Okay, so there we have our left rectangles. That's our approximation using 4 rectangles. Let's find the approximation for right rectangles. just to demonstrate this a little bit better here, I'm going to redraw the graph. Okay, but now instead of choosing the left endpoint, we're going to choose the right endpoint. So for each subinterval, we're going to attach the right endpoint to the curve and let that guide the height of each rectangle. Okay. So area. Now, if you look from the previous information here, notice how the width is all pi over 8, right? So what we can do is we don't have to write pi over 8 out every time. We can just factor that out. That could maybe save some time in terms of how much we write out. So if I factor pi over 8 out, then I can just spend the time to just add the heights one by one. So first rectangle, I don't want to choose f of 0. I want to choose pi over 8. So f of pi over 8 will dictate the height of my first rectangle. Second rectangle, I'm going to use f of pi over 4. Third rectangle, I'll use f of 3 pi over 8. And the last rectangle, I'll use f of pi over 2. So we see that for the first set of rectangles, we don't use pi over 2. We don't use pi over 2 because pi over 2 doesn't represent the left endpoint of any subinterval, right? So that gets left out. But for the right rectangle, it's the 0 that gets left out, right? Because 0 doesn't represent the height of any right side of any rectangle in our interval. Okay. Enter all this. You can take the time to plug into the calculator each of these values, or we can recycle some of the values that we found. But our right rectangle is going to be 0.7908. Okay. Look at the shape of the graph and look at the area that we've achieved. Okay. Here we're using left rectangles, but because of the shape of the graph, this we can also consider as what type of rectangles? What are some other types of approximations that we came across yesterday?
Midpoint.
Okay, good.
Upper.
Yeah, I wanted us to see that these are also upper rectangles, right? Also upper rectangles. So it's just kind of a coincidence, right? We can't always associate left rectangles with upper rectangles. It just so happens that's the case. How about here? Right rectangles are also what in this case?
Lower.
Lower rectangles. Okay. Again, that's not always the case. So this is just kind of like an observation thing. Why is it that for this problem, the left rectangles also act as upper rectangles? What is it about the curve that allows these two to be lined up so nicely?
It's downward sloping.
Downward slope. Because of the downward slope, the graph is always decreasing. If the graph is always decreasing, the left endpoint of each subinterval is always going to be higher than the right endpoint. So every rectangle that we draw is always going to sit above the curve. Okay. For the right rectangle, graph is decreasing, always decreasing. So the right endpoint is always lower than the left endpoint. So every rectangle that we create is also going to happen to be lower rectangles. Now, in what situation could maybe left rectangles be also lower rectangles? What do you think? When could these two behaviors line up? Or
When
these two?
X values are negative.
If it was like
Maybe.
a parabola,
Okay, can you be more specific?
if it rises on the right side and rises on the left side.
Okay, if the graph is always rising, then we're going to get a different relationship here. So I want to kind of point that out. It's nothing that we have to memorize, but it's just nice to kind of see that relationship, right? If the graph is always rising, then all of a sudden every left subinterval is going to be lower than the right subinterval. So what you're going to create are all these lower rectangles, right? Meanwhile, if the graph is rising, your right rectangle are going to end up being over approximations. Okay.
I guess I meant more on the left side of the graph. If you had like parabola.
Oh,
On
yeah,
either side.
I got it. Yeah. So now we can't line these up with these relationships if the graph is rising and falling all over the place, right? But in cases where the graph is just rising or just falling, we do see some potential symmetries in terms of relationship between left and lower, or left and upper, or right and lower and upper and right. So just want to kind of point that out to you, that sometimes they do line up, but those are, you know, we can only line those up if the graph has a nice kind of a continuous kind of motion, either always rising or always falling. Okay, so today we're going to be moving in the direction of getting from approximation to exact value. All right. So we're going to go to a formula on the next page, but before I get there, I want to talk about what the formula is doing and why the formula that you're going to see on the next page is going to feel so messy and complicated. And the reason why is because it's trying to do a lot of things all at once, and it's self-contained, and it's being really efficient in what it's doing. So I want to point out the things that we were kind of doing all by hand, okay, manually. First, we found the width manually, right? So we found the width, right? And then we took the time to take that width and add it to the left endpoint, right? We took the time to start at 0 because 0 is the left endpoint, and then we added each of the values by ourselves, right? We added pi over 8, we added another pi over 8, we added another pi over 8, another pi over 8, and each time along the way, we are assigning and naming each subinterval value. Okay, so we did this, and we also were plugging them into each of the height components of the area, right? So f of 0, f of pi over 8, f of 4 pi over 4, f of 3 pi over 8. And after that, we also then took the time to plug it into the function to get the actual height, right? We got it out of function notation, we plugged it into the function itself, got the actual height. And then we total all that together to get the area. Okay, so look at how many things we were just doing step by step, piece by piece. Now imagine if a formula was trying to do all this at the same time. Okay, we can expect it to be kind of complicated looking because it's just trying to do so many things at once. It's the formula we're going to see on the next page is going to find the width, it's going to do the incrementing for us, it's going to plug into the height component for us, and it's also going to find the height value for us. Okay, so I'm going to walk through the formula, but before I get there, I just want to show you, let's kind of make sure that we understand that it's trying to do a whole lot of things all at once. Okay, so next page. Okay, finding exact area using limits. Let's lead up to that point of conceptually. Let's say we had a curve, Okay, these are both the same curves, but one curve we're only using 4 rectangles. And the second curve we're using 8 rectangles. Okay, you can see that the 8 rectangle is going to be a better approximation of the region area under the graph. Right here with 4 rectangles, it's not doing a bad job because we're actually using midpoints here. So it's actually not doing a bad job. There's portions above and below, but we can see some significant gaps that are not being filled in, okay, whether it's above or below. But you can see that as if comparing between 4 and 8 rectangles, we have a much, right, the less rectangles we have, the better it's able to adapt to the sudden changes within the graph. And so that's why we have less of the gaps showing. So then if we take that idea and run with it, what if we continue to increase number of rectangles? What if we went from 8 to 16 to 32, to 100, 200, 300? We can expect the approximations to get even better and better. So then what if we just continue that idea and say, well, what if we just push the number of rectangles out to infinity? Then technically, shouldn't we be able to achieve not only a better and better approximation, but shouldn't we be able to reach the exact area under the curve? Okay, so that's the idea, is that if we have infinitely thin rectangles, then infinitely thin rectangles can adjust to all the changes that the curve is having, and it's going to be able to adapt and find every increment of our region, and not only get a better and better approximation, we should be able to achieve the actual area. Okay, so that's what we're going to be working towards. Now, because we're working towards infinity, we're not going to be stuck with just a constant value for n. We don't want to be stuck with just n equals 4 or n equals 6 or n equals 12. And because of that, we have to hold on to our n variable a lot longer. And because of that, our formula, our process will look a lot messier because we're not able to get rid of the n's as soon as we did on the previous page. All right, so let's talk about this area formula that we see in front of us. Okay. Limit as n approaches infinity, summation from 1 to n. This is going to do the work of eventually pushing out the number of rectangles out to infinity. B minus a over n, that's the width component of our area. We're going to be adding a bunch of rectangles together, but it's going to be all self-contained within this formula. Now, this b minus a over n is not all that surprising. We've been recognizing this as the width component, which is fine. It's the height component that looks really messy. Okay, so the height component is this f of a plus b minus a over n times I. Okay, so this looks messy because it's doing so many things for us along the way to help us get to that height of each of the rectangles. Okay, so again, I want to point out what I'm going to kind of talk about what this is doing here. It's taking that width, right? Just like how we were able to find that width of pi over 8. And then it's taking that width and it's adding to the left endpoint, right? We did that manually, right? We took that 0 and we added pi over 8. We added another pi over 8. We added another pi over 8. So that's what this is doing. It's taking that left endpoint, whatever that left endpoint is, and it's going to keep adding the next increment of the width. So it's going to add the width once to get to the first interval. That I is going to go to 2. So it's going to add another width component to get to the next interval. So what we're doing manually now is kind of all self-automated into this process, right? So it's going to keep adding the width to the left endpoint to reach the next subinterval, just like how we did here, right? Pi over 8 plus pi over 8 plus pi over 8. But now it's going to be plus the width, plus the width, plus the width. And then after it finds all these separate values, it's also plugging it into the function. Right? And we did that as well, right? We did that as well. We plugged pi over 8 into the function. We plugged 3 pi over 8 into the function, pi over 2 into the function to get all the specific height values. So it's doing a lot of things here. It's finding each of the incremental subintervals, and it's also plugging into the function to get the height. And then after that, then the height value gets multiplied by the width, and that will achieve the area of one rectangle. right? But we're going to be doing this over the course of, infinitely thin rectangles. So we're pushing this formula out to infinity. Okay. All right, so let's see if we can practice using this formula for this example here. Okay, example 1, find the exact area between 4 minus x squared and the x-axis. So we don't have to worry about what the graph looks like. We just have to kind of understand that we're going to be using this formula to help us find the exact area of this region. Okay. You're always going to be given your intervals, so you're always going to be provided your a and b values, left endpoint, right endpoint. And we're going to start inserting it into our formula. Okay, so b minus a over n, that's the width component. I'll just put this off to the side. Again, we're holding on to the n value because we don't want to be stuck with just a set number of rectangles, right? So 4 over n. All right, so here's our formula. There's our width, which is 4 over n. I calculated that already here. Times f of a, my a value is -2, right? We're starting at -2, and then from there, we're going to begin incrementing our width. Okay, width component, height component, but this is doing a lot of work here, getting each of the subintervals ready. All right, any questions so far? Okay, so just like how before we had to take those incremental subinterval x values and plug it into the function, we're doing the same thing here, right? We can't just rely on this and resolve this because this is just function notation. We need to have something that will tell us the actual height at each of these points. So we have to rely on this function, this 4 minus x squared, which is going to tell us the heights at every point that we need. Okay. But we have to somehow involve the argument into this function. And this is where I think students get stuck, not knowing exactly where that argument goes. So I'm going to help us kind of bridge that gap so we know exactly how to involve this with this function. So if you guys can write this down here, here's the function. The function is 4 minus x squared. We're going to take the time to reserve a space for where this argument is going to go. So if you can rewrite this function and leave a space where the x was, leave a parentheses where the x was, that way you'll know exactly where this argument is going to go. So I'm going to rewrite this as f parentheses equals 4 minus parentheses squared. Okay, everybody good with that? Every time I see an x, I'm just going to leave a set of parentheses there that will give it that reserved space for my argument. Okay, so now I'm just going to take that argument and insert it into where the space is. Right, so now I have a perfect substitution for my height component. I can take that and replace it with this. Right. I think that's the hardest part, trying to resolve this, get it out of functional notation, because once we're here, I mean, there's still some algebraic messiness involved here, but we're just going to clean this up. And once we get this cleaned up, it should feel like what we were doing on Tuesday, on our first day, where we were cleaning up, getting it ready for our summation formulas, involving the summation formulas. And then once we get everything in terms of n, then we looked at each fraction to compare degrees to identify the ratio of the coefficients and then just total them up and getting all the fractions added together. Okay, but yeah, now that everything's out of function notation, now we just have to now we can just worry about what we see in front of us. We don't have to involve anything to bring in. But there's still quite a few hurdles ahead of us. We have to make sure that we are expanding and cleaning this up correctly. We don't want to take that negative, distribute through, or combine anything with a 4. We got to resolve this parentheses squared first, but we don't want to just distribute this 2 through, right? That would be incorrect way of expanding. We have to FOIL this out. So I'm going to write this out twice so we can FOIL this out correctly. Okay, so this gives us 4 minus 8 over ni. Okay, so I want to make sure I bring it down the rest of my problem here. Okay, so once I FOILed this out, I combine like terms, but I still have this in a set of parentheses because I still have this negative sitting out here. So now I'm going to distribute the negative through, and eventually I can worry about combining with that 4. Okay, 4 minus 4 goes away. And then I can distribute the 4 over n through the rest of my terms. Okay, 4 times 16 is 64. Right, I'm multiplying denominator with denominator, so n times n gives me n squared, n times n squared gives me n cubed. Okay, so now this should feel more familiar. We have to assign, we're going to let each term have its own summation, and then we're also going to push the coefficients out in front because I want to isolate the summation I and summation I squared to get it ready for my summation formulas. Okay, everybody good so far? Okay, so I did 2 things at once. I assigned summation here and I also pushed the coefficients out in front. That way I can clearly see the rules that I'm going to be involving. Okay, so we go to the first page of our packet, get that summation I rule, which is just going to be n times n plus 1 over 2. And we also have a substitution for that summation I squared. n times n plus 1 times 2n plus 1 all over 6. Okay, I'm going to clean up each individual fractions here so that I can get a clear picture as to what the degrees and what the ratio of the coefficients are, since we're evaluating our limit as n approaches infinity. Now, I do want to point something out here. This second set of fraction, it seems really messy, right? Having to fold all this out and distribute the n through and the 64 through as well. So the bit of a shortcut is we only care about the highest degree, right? So the highest degree is just going to come from the first term of each section, right? So all you have to do is worry about that 64 with the n, with the n, with the 2n. Everything else is just going to kind of fall away. So if we were to multiply that out, you would get 128 plus ... The rest of the terms don't matter because they all have a lower degree. I mean, if we were to FOIL this out, you would get 1982 n squared plus 64n, but we can just ignore that, right? So we have a little bit of a shortcut. If we just multiply the first of each term that you see, that will get you to what you need to move forward with finding the appropriate limits. Okay, so first fraction, we identify the highest degree to be 2. So all that's left is just 64 over 2. Second fraction, only n cubed matters for us. Those are the highest. The lower degrees are not going to play a role in evaluating the limit. So just 128 over 3. So 32 minus 128 over 3 gives us 32 over 3. Okay,
Wouldn't
so
it
what
be
we
128 over 6?
Oh, sorry, over 6. My bad. Thank you. Copy that wrong. Thanks. Yeah, thanks for that correction. So 32 minus 128 over 6 gives us 32 over 3. So what we achieved here is not about the area. This is not only an approximation, this is the exact area. Okay. If we had substituted n a little earlier, let's say n was equal to 4 rectangles or 6 rectangles or 8 rectangles, the area will continue to move towards, will get better and better, right? So if we had a set number of rectangles, but we keep, let's say we tried with 4, then we went to 8, then we tried to 24, then 32. Each of the approximations will become increasingly more accurate. Okay? It'll get closer and closer towards this value, but now we've achieved the exact area because we've pushed the number of rectangles out to infinity. Okay. So this is a long process. Reason why we're going through this is because on the AP exam, sometimes you see problems that are asking students to interpret what this means or being able to understand the notation that's involved with this area formula. And it's also good for us to kind of understand that, that we are involving an area component, area of rectangle component. Okay, and also just getting understanding how limit plays a role in helping us achieve exact area.
Mr. Yang,
Yes.
so when we're doing the limit from n to infinity, why do we need to find like what does the same degree thing represent? Like comparing the ratio between the greatest degrees?
So comparing degrees, that's how we handled horizontal asymptotes, right? That's how we handled limits as n approaches infinity.
Okay.
Right? We always compare degrees. If it's a real number, we plug in, but if it's approaching infinity, we just always compare degrees. Yeah.
Okay. And that equals the area for these problems?
That's right. That gives us the area. Okay. So it's a long process. We will have a much more efficient way of getting to the answer using power rule. But the nice thing about this is that we can visually see how area plays a role in achieving our answer. Once we get to power rule, it's much more efficient, but it's also a lot more abstract. We're not able to see kind of like seeing the visual component of seeing this area kind of build from scratch. But because this is such a complex process, we're only going to be using relatively simple functions. Okay, we're not going to be dealing with problems with very high degrees. It's just going to be too messy to work with. But then once we move into our more abstract and much more efficient way of finding area, we're going to be able to also move up in terms of the complexity of our function and our problem. Okay, a few minutes remaining. I want to see if we can get started with another one of these problems because I want to be able to practice not only put into the formula, but getting our function notation out of function notation into an expression value. Okay, I think this is getting from here to here sometimes is where knowing where to put that argument value is where we get stuck. Okay, so here is, if you guys can go to page 11 in your packet. If you don't have the packet, you can just kind of copy this problem down. Okay, so here's our function, here are our bounds, and here is the area formula. 1 and 3 are area, are A and B values. So the width is B minus A over N. Okay, let's start putting into our area formula here. Width is 2 over n. Height component f of a. This is in function notation right now. Our a is our left endpoint, which is 1. And starting with 1, we're incrementing to the next interval we keep adding the width, right? Okay. Any questions so far? All we did right now is replace all the A's and B's with 1 and 3. Okay, the next step is we're going to have to find a way to get this to be easier to work with, right? Because right now these can't combine. This is stuck in function notation. We have to involve this function somehow because this is how we're going to arrive at the heights at every point on the curve. Okay, but we're going to spend time to bridge that gap. Okay, so let's rewrite this function here, or I'm going to write this function down here. F of x is 2x squared minus 3x plus 2. Okay, I'm going to spend the time to reserve the space where the argument is going to go. So wherever I see an x, I'm going to leave an empty space with a set of parentheses. And now I have a perfect place where that argument is going to go. Okay, did everybody see how we're able to take this function and insert those arguments in all the right places? Okay, so now let's make our substitution. We now have this height component in expression form. Right, any questions here? Out of function notation into something that we can begin to work with and eventually combine with the width. All right, piece by piece here. Want to make sure that we are expanding this correctly, right? We don't want to distribute the 2 through because the parentheses is not resolved. So we got to deal with this 1 plus 2 over ni squared, but we also don't want to be squaring and distributing the exponent through because that's not the right way of foiling, right? We have to write this out, write the parentheses out twice, and take the time to expand each of the terms. So I'm going 4 is 2 over ni plus 2 over ni. Okay, I'll bring down the rest of the problem here. Okay, and then next step, we're just going to spend the time to distribute through, combine like terms. And once we combine all like terms, then we can move towards summation formula and eventually get to the area. Okay, but I think the hardest part is behind us here because we fold this out and now it's just going to be distributing through, combining all like terms, and then also involving the width component as well. Okay, I have this worked out in the key. Maybe tomorrow I'll also kind of finish out the problem. We'll also need to go over trapezoid approximation, which is in 4.6, so we can skip the homework assignment for 4.6. You're just from 4.2. Okay. Any questions? All right, thanks everyone. Hope you guys have a great day. I'll see you tomorrow.
Thank you.
you.
Thank you.
Bye, Mr. Yang.
Bye, thank you.